Welcome to This Explainer. All right, let's jump right in. Today, we are breaking down a literal, epic chemical battle that is happening constantly all around us. Honestly, it's even happening inside us right now. It's the ultimate showdown, acids versus bases. We're going to look at what they are, exactly how they behave, and how they constantly fight for chemical dominance. Here is the game plan for today's showdown. We've got 5 rounds. Round 1 introduces our contenders. Round 2 looks at the lie detectors. Round 3 takes us straight into the reaction arena. Round 4 exposes their major shared weakness, the water dependency. And then we'll wrap it all up with Round 5, the power scale, ending in a pretty explosive climax. So let's kick things off with Round 1, the contenders, specifically definitions and taste. To bring chemistry straight into your kitchen and your bathroom, you have to notice how distinctly opposite these two really are. From a strict scientific standpoint, an acid is a generous donor. It donates H+ ions. A base, on the flip side, donates OH- ions. But let's actually make this practical. Think about taste for a second. Acids have this really sharp, sour taste. Imagine biting into a raw lemon. They also love to turn things red, literally a red flag for danger. Bases, conversely, have a bitter taste and this weird, soapy, slippery feel. Actually, think back to your childhood. Swear on your mother, or as the source playfully puts it, Mummy Kasam, you've definitely gotten bath soap in your mouth at least once, right? Remember that awful, bitter, soapy taste? Well, that is the exact taste of a base.
Now, to make these natural acids stick in your mind effortlessly, let's use a couple of brilliant mnemonic memory tricks. First, imagine a town called Very Acidic Orange City. Very acidic reminds us that vinegar contains acetic acid. Orange City reminds us that oranges and lemons contain citric acid. Pretty clever, right? And what if a friend asks you to play table tennis, or TT today? You just say, "No, TT, tomorrow." That instantly reminds us that tamarind has tartaric acid and tomato, tomorrow, has oxalic acid. It's just a remarkably effective way to lock these facts into your memory.
Moving right along to round 2, the lie detectors, or as they're known in chemistry, indicators.
So, how do we expose the true identity of these hidden chemicals if we obviously can't safely taste them? The source has this fantastic line for this. Today, we aren't just learning chemistry, we are taking a magic class. And it honestly really does feel like magic. Take a natural indicator like a hydrangea flower. Normally, it's blue. If you add an acid, it just stays blue. But the very second you add a base, it magically shifts to a vibrant pink. It's an instant visual lie detector.
We've also got synthetic and olfactory indicators. Phenolphthalein is a classic synthetic one. In an acid, it is completely colorless, but drop it in a base, and boom, bright pink. Methyl orange turns red for danger in acids and yellow in bases. But what about olfactory indicators? These are chemicals that actually change their smell. If you take onion extract or vanilla extract, you know they have really strong, distinct odors. But if you introduce a base, that smell completely disappears. The base literally destroys the odor.
All right, round 3, the reaction arena. Let's see what happens when chemicals attack.
When acids go on the offensive, they rely on very specific strategies. If an acid attacks a metal, it produces a salt and hydrogen gas, and you can actually test for this because the escaping hydrogen makes a distinct pop sound if you hold a flame near it. If an acid hits a metal carbonate, it creates salt, water, and carbon dioxide, which you can easily prove because CO2 turns lime water milky. Finally, if an acid reacts with a metal oxide, it makes salt and water. And this brilliantly illustrates a little secret. Because acid plus base equals salt and water, this specific reaction proves that metal oxides are actually basic in nature.
But hey, bases definitely fight back. Strong bases react with metals to create highly specific salts alongside hydrogen gas. For example, sodium hydroxide reacts with zinc to create sodium zincate. And the formula for sodium zincate is Na2ZnO2. The source gives a hilarious, catchy mnemonic for this one, not to, from the famous movie song. Think about it, Na2ZnO2. Na2ZnO2. Come on, it's totally impossible to forget. Furthermore, bases react with nonmetal oxides to create salt and water, which proves that nonmetal oxides secretly act as acids.
Which brings us to round 4, the water dependency. This is their ultimate weakness. You see, for all their destructive power, both acids and bases share a massive, crippling weakness. I'll pose this question directly to you. What do you think happens to these incredibly powerful chemicals if we remove water entirely? Just think about that for a second.
Well, the answer is they become completely powerless. A dry hydrochloric acid gas will not change the color of a dry blue litmus paper at all. Nothing happens. Why? Because acids and bases absolutely require water to dissociate. They need it to break apart into those active H+ and OH- ions. The source makes a really great comparison here. Think about how your behavior completely changes when house guests finally leave your home. You only show your true colors when the environment changes. Without water, these chemicals literally cannot show their true acidic or basic properties.
And now, we've reached round 5, the power scale and the climax. It is time for measuring strength.
Now that we know how they behave, we need a metric to measure their true strength in this showdown. Enter the pH scale, which stands for the potential of hydrogen. It's a scale running from 0 to 14, but there is a counterintuitive trick you've got to remember here. Because it measures H+ ion concentration, for acids, the lower the number, the higher the power. A pH of 1 is a far stronger acid than a pH of 5. Conversely, for bases, the higher the number, the stronger the base.
And sitting smack in the dead center is the number 7. This is pure, neutral territory. If you use a universal indicator, a pH of 7 glows a perfect balanced screen. It is neither acid nor base.
Now, this chemical battle of the pH scale isn't just lab theory. It dictates our everyday lives. Take digestion. Our stomachs actually rely on powerful acids sitting between pH 1 and 3. When that gets out of hand, we take antacids, like milk of magnesia, which is a base, to neutralize it. Out in the farm fields, soil needs an optimal pH of 6.5 to 7.5. If the soil gets too acidic, crops die, so farmers add quicklime, a base, to fix it. Even when a bee stings you, it is injecting acid right into your skin. That burning pain is acidic, which is exactly why your mother might have rubbed baking soda, a base, on the sting to bring relief.
Another incredibly important number on the pH scale is 5.5. If the pH inside your mouth drops below 5.5, the environment becomes so acidic that your tooth enamel literally begins to corrode. And that is exactly why our daily toothpaste is formulated as a base, to scrub away the acid and protect our teeth. Which finally brings us to the epic climax of our showdown. What happens when our two heavy-hitting contenders clash directly? It's called neutralization. When an acid and a base combine, fire meets water. They completely destroy each other's distinct chemical properties, leaving behind just two simple things, a neutral salt and water. The battle essentially ends in a perfect balanced draw. But to wrap up this explainer today, I want to leave you with a little puzzle, a provocative thought to test your new knowledge. We just learned that a strong acid and a strong base create a perfectly neutral salt. But what kind of salt is born when a strong acid battles a weak base? Who wins that subtle tug of war? Think about the balance of power we just discussed. Thank you so much for joining me for this explainer, and definitely keep exploring the amazing chemical showdowns happening all around.